So let us see how we can be able to understand the racing case or the racking case of the linear motion. Now, let's say we have the object. Let's say this is the object 1. And we have another object. Let's say this is object 2. And assuming that the both objects are moving in a linear path given as that. And say the object 1 is moving towards that direction. And our object 2 is moving in this direction. So which means the object 1 is chasing the object 2. That is behind the object 2. So now, let's say the object 1 is behind the object 2 with about 20 meters. And let's say the object 1 is moving from rest, which means initial velocity is let's say it is moving at a constant rate of 12 meters per second square. Let's say that's the case. And say the object 2 is moving at a constant speed given as, let's say, a 15, now should be given as, let's say, 20 meters per second. Let's say that's the case. Now the point of interest is when object 1 overtake or catch object 2, and after actually when will that one be happening, and after in which the distance, or how actually what is the distance in which the object 1 have to travel in order to catch object 2. So that's the principle behind the racing case of motion, or we call it as a lagging case of motion. So now, just like though we discussed about the head-on case of the linear motion, so now the analysis also be the same in this case. So make sure that before this one you should have to watch about the racing case. Actually, the lagging actually should be head-on case of the motion, because we can have to use the analysis we actually discussed about that. Or just have to go through the video I made about applications of linear motion. It's about closer to 1 hour soon, but it's something helpful. So we don't know the time takes for the object 1 to travel, and even the displacement given as S1 we don't know. And what is the actual time takes for the object 2 we don't know. And what will be the distance traveled by the object 2 as it will be catched by object 1, we don't know as well. But the good news is that we are being given the separation distance between the two objects, in which the object 1 is behind the object 2 with. So that is separation distance, we call it as a lagging parameter or a racing parameter, because the object can be behind the other in terms of distance or the time. So whenever the object is behind the other in terms of distance, then we say the lagging parameter is a distance. And whenever the object is behind the other in terms of time, then we say the lagging parameter is actually a time. But in the analysis, we need to have the lagging parameter as the distance for the effective actually understanding, or actually for the effective analysis, or for the effective actually way out of our actual problem. So keep that in mind, and you should have to understand that this is actually a separation distance has been covered by the object 2. So take note of that. So which means for the object 1 to overtake object 2 or to catch object 2, first thing you should have to cover the separation distance. Then you should also have to cover the distance in which the object 2 was covering when the object 1 was covering the separation distance. That's the essence behind. So for the object 1 to overtake object 2 or to catch object 2, which means it has to cover the distance, it has to cover 1, the separation distance, and also the distance in which the object 2 covered when the object 1 was covering the separation distance. Mind you, what is happening is that both objects are in motion. The moment in which the object 1 is covering distance, after this distance, the object 2 is also in a motion, in the sense that the time takes, in the sense that the term in which the object 1 is covering the separation distance. Actually, object 2 is also covering some sort of distances. So which means in order for the object 1 to catch object 2, it has to be in the way that it has to cover the separation distance as well as the distance covered by the object 2 the moment the object 1 was covering this distance. So keep that in mind. So the point of interest is, when will the object 1 catch up object 2, and after what distance? So that's the principle behind this. So now, according to the displacement formula, what is displacement for object 1? We have it as 6t squared, so which is given as equation 1. And how about the displacement for s2? We'll have it as 20t, which is given as the equation 2. Mind you, before this lesson, make sure that you watched about actually the racing should be the head-on case of the actually a linear motion, or you just have to go through the applications of kinematics, because that's where I explained much about this. So in this case, we need to have the damped x in which the one has to travel that way. So you have to understand that the s1 is the same as the separation distance plus s2. So which means for the object 1 to travel to catch object 2, it has to cover the separation distance, and the distance the object 2 covered, the time the object 1 was covering this. So with that, then we'll be able to have the damped x. So we'll have it as this now. So that will happen is that what will happen is that we'll have 6t squared and plus that is being given as 20. Now we should have it 16. Should be 60. It is 60 squared is equal to 20 plus 20 actually t. That's what will happen. Then I'll have that one as the quadratic actually equation. So in the sense that we have it as a 6t squared and a minus 20t, the minus 20, which is equal to 0, of which we can further simplify the expression. We'll have it as a 3t squared and the minus 10t and the minus 10, which is equal to 0. So now be able to solve for t using the quadratic formula, in the sense that we have a being given as 3 and the b is given as the negative 10 and the c is given as the negative 10 as well. Then I should have to plug in these values in the quadratic formula, and that will be given as a t is equal to negative b plus or minus the square of b squared minus 4ac divided by 2a. So in this case we'll have it as a positive 10 plus or minus the square of, now have it as 100, and then negative 4 times a, we have it as should be 12, in times 10 we'll have it as a positive 120, and that divide by should be now 6. That's what will happen. Then what follows next? And of course we can have it as this. So now which means we'll have 100 plus 120, or have the term being given as 10 plus or minus the square of 220 and that divide by 6. So in this case we'll have it as, what is the square of 120? So what is the square of 120? Of which you can have it as a 10.95, of which we can have it as 11. So which means we'll have it as 10 plus or minus 11 divided by 6. So in this case, we'll go for the value of t that will be positive, because our time can't be negative. So which means we'll have t is equal to 10 plus 11 divided by 6, and of which we'll have it as we can have it as that divided by 6. We'll have it as 3.5. That is the time. We'll have it as 3.5 seconds. That's the time in which the object 1 has to travel to catch or overtake object 2. So take note of that. And how about the distance it has to travel? So now the distance for S1 will be given as, upon having substituting to the displacement formula, the distance formula for the object 1 we already presented. That will be given as 60 squared, that is the same as 6, 3.5 to the power 2. So try to have that one out. And also the distance for object 2 also have to substitute in the same way. So take note of that. And how about the speed of the object 1, the point in which it is going to overtake object 2? We can also have in the same way using the equations of kinematics, the way we discussed in that of the head-on case of the linear motion. So bear that in mind. So now, what if the racking parameter is given as the time? Let's say we had about 2 seconds. Let's say the object 1 is behind the object 2 about 2 seconds. So now, let me have it in this way, and say this is somewhat a new concept. Let me give you another values here. In fact, you should be able to understand what is really happening here. So now, given a typical problem case, and now it should be like this, of course. Let me start it afresh. So in this case, let's say the object 1 is behind the object 2 about 2 seconds. And let's say the object 2 is moving, let's say from initial velocity given as, let's say, 2 meters per second square. Let's say moving at a constant rate of, let's say, 10 meters per second square. By the way, this has to be just that of meters per second, because that's the velocity. And let's say the object 1 is moving, let's say, at a constant speed given as, now should be about 50 meters per second. Let's say that should be this. Let's say about 20 meters per second. Let's say that's the case. So now, what is the time takes for the object 1 to travel to overtake object 2 and the distance traveled? So I don't know the time takes, and I don't know the distance covered for the object 1, and for the object 2 we don't know the time takes. Don't dare to say this is the time. And we don't know the distance traveled given as S2 for the object 2. But what is the principle behind? So S1 will be given as 20 g. That is the equation 1. And S2 will have it as 2d plus, now should be 5d squared given as the equation 2. And what is the, now we have the racking parameter being given in terms of time, but we need it to be in terms of the distance. What should we do? But you should have to understand that this time has been covered by the object 2. So in order to have the separation distance given as st, then I will have to substitute t into the distance formula for the object 2, in the sense that we'll have to substitute it into this one. So where there is t, we're going to have that time. In that case, we'll have it as 2. Now have it as 4 plus 20. That will be given as 24 meters. So which means at 2 seconds is corresponding to half as 24 meters. So that's how we find the separation distance if we are being given the lagging parameter as the time. So we substitute the time into the distance formula for the object 2. Keep that in mind. So which means we'll have S1 plus S2 is equal to 24 meters. So you'll be able to have the time and finish it off with the way we are doing it there. So take note of that. So that's how the ranking case or the chasing case is being analyzed given the typical problem in that case. Thank you.